Today we're going to continue our discussion on derivatives and the special rules that we have depending on the type of function that we're going to take the derivative of. Before we get too far into that, just a quick little reminder of some of the rules that we looked at yesterday. We're going to start by doing another practice problem with our power rule. So remember, our power rule says, okay, if you want to take the derivative of x to some power n, then that's going to be n times x to the n minus 1. And then any coefficients that we have in front, they just get multiplied by. So if I have the derivative of 3x squared, that's going to be 6x to the first, or just 6x, because we bring the 2 down, multiply by our 3, and then we drop 1 in our degree. So we are going to do an example. We're going to take our derivative of the square root of x. And you might be looking at that and immediately you think that's not a power. But if you take a minute, you'll realize that that actually is going to be using our power rule, because rational functions, rational expressions can be written with exponents. They're fractional exponents. So this is just asking us to take the derivative of x to the 1/2. So we bring down that exponent as a coefficient out in front. So we have 1/2 x to the 1/2 minus 1. We subtract 1 in that exponent. So I get 1/2 x to the negative 1/2. And depending on how the directions ask you to leave your answer, you could be done there. Or we could write this as 1/2 times 1 over x to the 1/2, or 1 over 2 times the square root of x. That works as well. So there we have the derivative of the square root of x, 1 over 2 times the square root of x. And we actually did this derivative a couple days ago with the limit definition of the derivative with our quotient rule. And if you recall, that took quite a bit more time than what we just did right here. All right, one other rule that we're going to review before we continue our discussion is the product rule. So the product rule is what we use if we want to take the derivative of two functions multiplied together. So f of x times g of x. And we had a little song to help us remember it, our little song or our little ditty. It revolved, okay, we'll call the first function 1 and our second function 2. We end up with 1d2 plus 2d1. So in terms of our function notation, and I'm going to use my prime notation here, this is going to be f of x times g prime of x plus g of x times f of prime of x. And we have to use this rule if we're ever doing the derivative of product. I cannot, no matter how much I may want to, no matter how much it may seem to be nicer and more helpful or whatever it is, I can't just say f prime times g prime. It doesn't work that way. It doesn't work that way. So we're going to do an example. We're going to take the derivative, and you can pause and try this on your own first and then hit play and see if you match, but we'll take the derivative of x squared times e to the x. So I'm going to label them 1 and 2 to help me here, and I've got my rule 1d2 plus 2d1, and I say that every time I take a derivative, no matter how many years I've been doing this. I always say 1d2 plus 2d1. So I have 1 times d2, the derivative of my second function, is the derivative of e to the x, with the derivative of e to the x is just e to the x, plus my second function, e to the x, times the d1, because it's 2d1, derivative of x squared is 2x. And because of things long ingrained in my life, I am going to rearrange things just slightly. Keep x squared e to the x the same, but I'm going to make it 2x e to the x. And that's my final answer. And no, I cannot combine those. They are not like terms. I got an x squared and then an x there. I could, if I wanted to, factor out e to the x, and I can make this x squared plus 2x times e to the x. Don't need to do that though, but I could. All right. Today we will be talking about the quotient rule and how we handle taking the derivative of a quotient. But before we get to that, we're going to talk about how we can use derivatives to find or locate maximums and minimums on polynomials. And we actually do this quite often in calculus. This is a very common problem that you're going to see in AP Calc. But what we're going to do is, using our derivative, we are going to find we call it the extrema, or the relative extrema. So the high and the low points of a function. So we're going to look at the function y equals negative 3x squared minus 12x plus 14. And not only will we be able to figure out where my high or my low points are, but I'll be able to figure out what type it is. And now we know things about this function already. We already know by looking at the equation that it is a parabola. And it is a parabola that opens upward. So we know that we should find a minimum, but we are going to prove that using our calculus and what we know about derivatives and increasing, decreasing, and how that has to go along with our positive tangent slopes and negative tangent slopes and all those things to help us prove that it actually is a minimum without seeing a picture, without seeing a graph. Okay. Now, we're not going to graph this right now, but I do want to think about the shape of maximums and minimums. And think about, okay, if I have a max, that's going to be like a high point. Or if I have a min, it's a low point. But at either of those points, if I think about the tangent lines at those highs and low points, my tangent lines are going to be horizontal. So extrema, our relative extrema, our maxes and our mins, have horizontal tangent lines. And that's key, because horizontal tangent lines are going to have slopes equaling to 0. Horizontal lines have 0 slopes. So if I have a horizontal tangent line, my tangent slope at that point needs to be 0. But if you recall, the derivative is the instantaneous rate of change, or it is the slope of the tangent line at a given point. So when we're looking for our highs and our lows, when we're looking for our relative extrema, our maxes and our mins, we are looking for where we have horizontal tangent lines, which means we're looking for where y prime, my derivative, equals 0. We're going to make that grammatically correct, actually. So we're asking, where is the derivative equal to 0? And when we ask where in mathematics, we typically are saying an x value. We'll figure out the y value later, but I want to know what x value makes my derivative equal to 0. So in order to do that, the first thing I'm going to do is I'm going to take my derivative, or I'm going to find my f prime of x, or in this case, since it's a y equals equation, I'm going to find y prime. That's the first thing I'm going to do. So my y prime, using a bunch of my power rules over and over again, is going to be negative 6x minus 12. Remember that the derivative of a constant is always 0. And now I have my derivative. This is the equation that's going to produce tangent line slopes over and over again. Pick an x value, get your tangent line slope. Pick an x value, pick your tangent line slope. So we're trying to figure out, where is this derivative? Where is y prime equal to 0? So the second step we're going to do is we're going to set y prime equal to 0. So we're going to have negative 6x minus 12 equals 0. And then our third step, I'm going to put it over here because I want to use that space below. We're going to solve for x. And depending on the polynomial you begin with, you're going to have 1, 2, 3. You'll have potentially multiple x values where this equals 0, which should make sense. Think about if you have a cubic, you're going to have both a max and a min, potentially. Potentially you'll have both a max and a min. So you should have multiple x values that have a derivative of 0. For us, for our parabola, we're only going to have the 1. So I have my equation. I want to set it equal to 0, and I want to solve for x. So I'm going to get negative 6x equals 12. So x equals negative 2. And then step 4 is going to be determining if it's a max or a min. And so the way we're going to do this is we're going to use what's called a sign chart, an SIGN chart. So I'm going to make my chart. I'm going to have one line, one location on my chart, and that location is x equals negative 2. And this is a chart for f prime, or I guess for our purposes, y prime, since our equation is a y equals. What I want to do is I want to figure out if I am on the left of negative 2, if I'm on the left side of x equals negative 2, is my derivative positive or negative? Remember, if your derivative is positive, that means you have a positive tangent line slope. And if I have positive tangent line slopes, we are going to be increasing. So remember, if y prime is positive, then y is increasing. And we're going to make that a little bit more organized. All right, so if y prime is positive, then y is increasing. And if y prime is negative, then we have these negative tangent line slopes. Y is decreasing. So by figuring out if my y prime is positive or negative, on either side of what we call a critical number, and you don't really need to know that term right now, but in calc you're going to know that term, so keep that in the back of your mind, critical number there. If I'm increasing on the left side of x equals negative 2, and then I'm decreasing on the right side, you can see how that's going to be a maximum. Versus if I'm decreasing on the left side, but increasing on the right side, that would produce a minimum. So what we're going to do is we're going to test some points to the left and to the right of x equals negative 2 into y prime. Into y prime. So this is a y prime sign chart. So I've got my y prime up here. And I'm going to, on the left of x equals negative 2, I'm going to pick the number negative 3. I can pick any number I want on the left of negative 2. That's fine. But we're going to pick negative 3, which means y prime is going to be 18 minus 12, or 6, positive 6. So on the left of negative 2, y prime is positive. On the right-hand side, I'm going to pick the number x equals 0. 0 is to the right of negative 2. So y prime is equal to negative 12. So to the right of negative 2, my derivative is negative. If I were then to translate what that means in terms of my function y, positive derivatives means y is increasing. Negative derivatives means y is decreasing. So that green set of arrows is giving me that idea that we're climbing. At negative 2, we plateau because that's where my horizontal tangent line is. So that's where my derivative is 0. And then we fall down. So think about a mountain. We're climbing up the mountain. We hit the top. We come down. That right there, because y prime changes from positive to negative, at x equals -2, y has a relative maximum at x equals -2. That's what we can say. We found the maximum value. Well, we found the x value for the maximum point. Our last step, step 5, is find the output, the y value at the x value. So to use this, we're going to use the y equation, because remember our y equation, that is what gives us those original outputs for our inputs. So we're going to use that y equation, that's all the way up there at the top, that -3x² minus 12x plus 14, and I'm going to substitute in my -2. So y is going to equal -3 times -2² minus 12 times -2 plus 14. And I should have remembered what my answer was before, but I don't remember. 26. Which then gives me the coordinate pair, -2, 26, as the maximum location. So the actual maximum is 26. So if this was a price function or a cost function or something that had a real world application, we would say your max is $26 a day, or your max is 26 computers that can be made, or whatever it is that we're trying to do. So there we go. So big idea here is maxes and mins, those relative extrema, are going to occur where your horizontal tangent line is, or where your tangent line is horizontal, and that's going to occur where your derivative is 0. So this is the big idea. Where is the derivative equal to 0? This step 4 is just showing that it's truly a maximum, not necessarily a minimum, or a minimum, not necessarily a maximum. And then this sentence here is what they're going to look for in calc for your explanation. All right, you're gonna learn about the sign chart in calc and all of that stuff. But on the AP test, I'm going to tell you, no AP grader is going to look at that. So that's sort of for your own, work your own help there. They're going to look at your conclusion sentence that you're going to write. So that's what you're going to practice quite often in AP Calc. All right, we are now going to move on to our quotient rule. Quotient rule, a lot of fun. Not everybody loves the quotient rule. I love to sing it. It's got its own little rhyme, just like the product rule does. So product rule, remember, is 1d2 plus 2d1. Quotient rule, a little bit more involved. Okay, but we still have a nice little rhyme to help us. So this says, okay, you want to take the derivative of something like f of x over g of x. How are you going to do that? It's not just f prime over g prime. Would love for that to be the case, but it's not. It just isn't, unfortunately. We have another way to do this. And so what I'm going to do is, instead of using f and g, as much as we love that, to make things a little bit simpler and to go with our rhyme, I'm going to change this. And I'm going to call the top function the high function, and the bottom function the low function. Not very mathematically rigorous, but it's going to be a little bit easier for us to follow. My rule, or the quotient rule, not my rule, but the quotient rule, is low d high minus high d low all over the square of what's below. That's your quotient rule. Low d high minus high d low all over the square of what's below. It's a little bit more involved than our product rule. But it's still fun to say. Actually, I think it might be more fun to say. 1d2 plus 2d1? Nah. Low d high minus high d low all over the square of what's below. We always start low. All right, I don't know how else to remember it, but you always start low. Low D high. This time we are subtracting rather than adding. That's a big difference between the quotient rule and the product rule. And then the denominator is being squared. So again, when you do your quotient, you end up with another quotient back. And so it still starts to build on itself. Sort of like when you do the derivative of a product, you get a product back. You do the derivative of a quotient, you get a quotient back. Okay? Your D high and your D low, those are the derivatives, those individual derivatives. So just keep that in mind. We have our low D high minus high D low all over the square of what's below. So we're going to do some examples. We're going to use this. All right, so first example. I'm going to take our derivative of 2 over 2x to the fourth minus 5. So I'm going to label in blue. Here is my high. Here is my low. So following my pattern, we're going to start with a low. And I'm going to use parentheses, 2x to the fourth minus 5. It is the original function in my denominator. Times the derivative of my numerator. The derivative of 2, a constant, is 0. Minus high, my original numerator, so 2, times the derivative of my denominator is a polynomial, it's a product rule. It's going to be 8x cubed. That negative 5 is going to go to 0. We lose that. We drop that off. And this is all over the square of what's below. So 2x to the fourth minus 5 squared. We're going to clean this up a little bit. This whole thing right here is going to go away. I have something times 0. The 0 is canceling it out. It overpowers it, and it's gone. So my numerator is negative, and I'm going to multiply the 2 and the 8. So negative 16x cubed over 2x to the fourth minus 5 squared. And there's my derivative. And again, I have a quotient. This one was nice because I was able to lose one of my terms in the numerator, and so I just have a single numerator over a denominator, but I still have a quotient. So if I wanted a higher order derivative, a second derivative, or third derivative, I'd have to continue doing my quotient rule. Still a lot easier than doing my difference quotient. Imagine doing the difference quotient on this. Oy, doesn't seem very fun. All right, now we're going to take another derivative. We're going to do d dx, take the derivative of 4x cubed minus 3x squared over 4x to the fifth minus 4. And again, you may not need to do this, but I'm just going to label them high and low. And I'm going to zoom out. There we go, so we can see our rule up above. High over low. All right, we start low. 4x to the fifth minus 4 times d high, so the derivative of my numerator, the derivative of my top function, which is going to be 12x squared minus 6x. Unfortunately, this one doesn't go away, so no 0 there. Minus high, my numerator, 4x cubed minus 3x squared, that original function. D low, so the derivative of my denominator, is 20x to the fourth all over the square of what's below. So 4x to the fifth minus 4 squared. And you could distribute your numerator, combine like terms, see if anything cancels, and sometimes it will and sometimes it won't, and you might be like, oh look, common factor, but remember we've got that minus over here, so we'd have to see that common factor on the right hand side as well before we can do any canceling. So we're going to stop there, but you could clean that up, you could combine like terms and make it a little bit simpler. All right, we are now going to look at some trig examples. We're going to take the derivative of our tangent of x. And again, you might look at that and be like, there's no quotient there. It's just tangent. It's just a function. But remember, we have these different identities, these things that have to be true. One of them being that we know tangent can be written as sine of x over cosine of x. You can write tangent as a quotient. So to find the derivative of tangent, we can change it into the derivative of a quotient of sine and cosine, which we know the derivatives of, and we can do our quotient rule. So I have my high function, I have my low function, and I can do my derivative rule. So high d low, we always start low. Low d high minus high d low all over the square of what's below. So this is going to be cosine x times the derivative of sine of x. The derivative of sine of x is cosine x minus high, so sine of x, times the derivative of cosine of x. The derivative of cosine of x is negative sine x all over the square of what's below. So this is going to be cosine squared x. This one, I'm going to clean this up. This negative here and this negative here are going to become positive. So I'm going to get cosine squared x plus sine squared x all over cosine squared x. And we have another identity. Cosine squared plus sine squared is 1. So this is just 1 over cosine squared x, which I'm going to actually rewrite as secant squared x. And so we get that the derivative of tangent of x is secant squared x. Using our quotient rule. All right, we're going to do one more. Last one we're going to do is similar. We're going to do d dx, the derivative of cosecant x. And so you're going to rewrite it, put it into a quotient form first. All right, make it into a quotient first. So we're going to write this as its identity, 1 over sine of x. And you might be like, well, that's not really simpler, but it is a quotient. We know the quotient rule. So we don't know cosecant x, the derivative of that. And we could try and do the quotient rule, but we're going to end up with the same issue of sine and cosine. And so what we're going to do is we're going to write it in terms of sines or cosines, the ones we know are derivatives of, and use either a product rule or a quotient rule or whatever rule we can. So using my quotient rule here, using my quotient rule, I'm going to have low d high minus high d low. So then remember the derivative of 1 is 0, the derivative of sine is cosine, all over the square of what's below. Well, 0 is going to cancel out. It's going to wipe out my sine of x, and I'm going to get negative cosine x over sine squared x. And I'm going to play around with this a little bit. What I'm going to do is I'm going to write this as negative cosine x over sine of x times 1 over sine of x. I'm going to do that. I'm going to split that denominator. And then looking at that, using some identities, negative cosine over sine is negative cotangent, and 1 over sine is cosecant. So we get that the derivative of cosecant, I'm going to make that look like an S, of x is negative cotangent times cosecant. And there's our derivative, all using our quotient rule. So, quick reminder, quotient rule. Make your numerator, call that high, denominator low, is low d high minus high d low, all over the square of what's below.